Hey everyone, and welcome right back to The Explainer. Today we're diving into something that is absolutely mind-blowing, the microstructured world of modern smart textiles. We're not just talking about putting a fitness tracker on your wrist. We're talking about clothing acting as a living, breathing technological organism. I am super excited to guide you through this, because the engineering that's transforming the literal shirts on our backs into highly advanced computing interfaces is just incredible. We're going to break down the anatomy of what researchers are calling thinking fabrics. We'll be looking closely at the physical, digital, and networking systems that actually make all of this possible.
Okay, so to really appreciate where we are right now, we kind of need to see how we got here. Think back to the first generation of wearable tech. It was basically clunky, rigid electronics, heavy, boxed sensors that were literally just taped or strapped onto passive, normal clothing. By the second generation, things got a bit more integrated. The fabric became an active substrate, which meant engineers started interweaving or gluing discrete components directly onto the cloth using conductive adhesives. But what we're analyzing today, this is the third generation. The textile itself is a holistic computational medium. The electronics aren't just attached to the fabric anymore, they literally are the fabric, engineered right down to the microscopic fibrous substrate. And really, that brings us to our primary definition for today's explainer: thinking fabrics. Basically, these are textiles engineered right at the fiber level to actually possess electrical and computational properties. This completely shifts the entire paradigm. The cloth itself acts as a holistic human-computer interaction interface. The sensing, the actuation, the data processing, it's all intrinsically woven right into the material. It's essentially a system-on-fiber core that turns your everyday hoodie or t-shirt into a continuous real-time biometric and environmental monitor.
So, to wrap our heads around this incredibly complex organism, here is our roadmap. We'll start with the textile hierarchy. Then, we'll see if it can survive the spin cycle, dive into on-body edge computing, check out a software showdown with Rust versus the microcontroller, and finally map out the I4C dynamic network. Let's get to it.
Section 1. The textile hierarchy. Physical foundation.
To pull off seamless electronic integration, you have to engineer things at every single tier, building it literally from the bottom up. Step 1 is the fiber itself, the absolute basic construction block. Researchers are actually creating system-on-fiber cores where nanomaterials are bonded at the molecular level. Step 2 is the yarn. This is where those fibers get spun together into composite electroconductive strands that can actually carry data and power. And finally, step 3 is the fabric phase. Here, those highly engineered yarns are woven or knitted into stable, resilient networks. They can even be embroidered to form actual physical logic components.
But of course, there is a massive existential threat to this beautifully engineered system. The real world is messy. Research points out that E-Textiles are highly vulnerable to physical deformation caused by repeated wash and wear. Think about it. If a standard circuit board is meant to live inside a hard plastic shell, how on earth is it supposed to survive the daily chaotic life of a t-shirt?
Which brings us to Section 2, surviving the spin cycle, E-Textile washability.
If you're a microchip, your standard household washing machine is basically an extreme testing centrifuge. It's a torture chamber. First, you've got mechanical stress from the drum rotation and agitation, which violently throws the circuits around. Then there's thermal stress, where hot water causes all those tiny materials to rapidly expand and contract. On top of that, you have chemical stress. The detergents and alkalis are relentlessly attacking the conductive coatings. And finally, drying stress from the intense heat and tumbling of a machine dryer. Honestly, it's a miracle any electronics survived this whole shebang.
And the physical realities of washing these E-Textiles, they are bizarre and super counterintuitive. You'd probably think, hey, just use a gentle, low-speed wash, right? Well, real-time video analysis actually shows that at low speeds, like around 34 RPM, the fabric gets repeatedly pulled up and just dropped by gravity. That causes severe impact damage and up to 30% thread loss. Conversely, if you crank it to high speeds, say 800 RPM, the centrifugal force pins the fabric nicely to the drum wall, which minimizes impact drops. But the intense vibration at that speed can completely rip encapsulated chips right off the fabric. So the engineering workarounds are wild. Get this, simply tossing the smart garment into a standard laundry bag increases circuit board survival by a massive 89%. It's such a simple fix for such a complex problem. Plus, engineers have to use highly specific encapsulation techniques like glob-top resins or stretchable PDMS adhesives that are perfectly matched to the specific mechanical demands of whatever wash profile the shirt will go through.
All right, let's move from the physical to the digital brains of the operation. Section 3. On-body edge computing, digital architecture.
We are right in the middle of a massive paradigm shift toward on-body edge computing. See, instead of your shirt just dumbly sending raw biometric data over to your phone or up to the cloud to be processed, the data is processed directly on the garment itself. The fabric literally operates as a decentralized data mesh. So maybe your sleeve is a dedicated node for gesture recognition, while a chest panel is entirely focused on cardiac monitoring, acting as its own autonomous computational node. This is absolutely crucial. Why? Because it guarantees absolute data privacy, drastically lowers the latency so you get real-time feedback, and it completely removes the need to constantly pair or connect to external hubs. But wait a second, how do you compute without a traditional rigid circuit board? Well, you sew one. I'm serious. You literally sew it. One of the absolute coolest breakthroughs right now is embedding programmable logic arrays, or PLAs, directly into the fabric. Engineers are using conductive thread stitching to actually embroider functional logic gates, your standard and, or, and not gates, right into the warp and weft of the cloth. And by just changing the stitching connections, these Boolean circuits can be totally reconfigured on the fly for personalized health monitoring. Plus, by layering these PLA layouts, they drastically reduce the chance of short circuits, which makes this computational fabric incredibly reliable.
Section 4. Rust versus the microcontroller. Software showdown.
So, let's talk code. When you're programming for tiny, low-power ESP32 microcontrollers that are sewn into a shirt sleeve, the programming language you choose is absolutely everything. On one side of the ring, you have MicroPython. Now, MicroPython is awesome because it's highly developer-friendly, it's fantastic for rapid prototyping and education, but it really struggles with the intense real-time execution speeds that smart textiles demand. On the other side, you have compiled languages, specifically C, C++, and Rust. These languages deliver the blistering high performance needed to handle incredibly strict latency requirements, and that speed is totally non-negotiable if, for example, your shirt is trying to give you real-time haptic feedback based on your muscle movements.
Just to put that performance gap into perspective, 30 times. Yep, 30. That is the dramatic execution slowdown our source data measured when engineers tried using MicroPython to process intensive tasks, like secure hash algorithms, compared to a baseline C implementation running on that exact same ESP32 microcontroller.
Looking at the numbers, if we use C or C++ as our baseline speed at 1.0x, we can see that Rust is right there on its heels at just 1.1 times slower, practically identical. TinyGo is also super efficient, sitting at 1.3 times. But then look at MicroPython trailing way out there at 30.0 times slower. When your garment is constantly crunching rapid fast Fourier transforms or running cyclic redundancy checks to monitor a real-time heartbeat, a 30x delay? Yeah, that is simply unacceptable.
So why is the industry leaning so heavily toward Rust as a superior choice over the traditional standard of C? 2 words: memory safety. Rust balances the raw, blistering speed of C with an incredibly strict memory safety net. It requires zero runtime or garbage collector, which makes it absolutely perfect for running performance-critical tasks on these low-resource textile nodes. But most importantly, Rust has this unique ownership model that essentially guarantees memory safety, totally eliminating a massive class of compile-time bugs. Think about it. In a highly variable, constantly stretching, and moving E-Textile environment, preventing a software crash is literally paramount. You absolutely do not want your smart jacket to blue screen on you while you're wearing it.
Which leads us to the nervous system. Section 5. I foresee a dynamic network.
Okay, here's a massive engineering headache. How do you get these threads to communicate with each other in a shifting, completely deformable network? I mean, traditional circuit boards are static, they just sit there. But a clothing network bends, it folds, it stretches, modules are hot-swapped constantly, maybe you snap a new heart rate sensor onto your jacket, or take a battery module off before you wash it. Every time you do that, it changes the total electrical capacitance of the entire fabric bus in real time. In a traditional setup, those constant changes would instantly crash the standard I2C communication protocol.
So, what's the fix? It's a brand new protocol called I4C. And what it does is actively measure the bus rise times in situ, directly inside the fabric. As the number of target devices on the bus changes, like when you plug in new sensors into your jacket, the system instantly detects that shift in capacitance. It then automatically adjusts the pull-up resistors on the fly. It'll drop from 10 kiloohms down to 4.7 and then maybe down to 2.2, all just to ensure the communicational signal stays perfectly stable. It adapts in real time.
This I4C protocol is a giant leap forward for smart fabrics. First off, it's totally backwards compatible with legacy I2C devices, so engineers don't have to just throw out the old tech and reinvent the wheel. That real-time pull-up adjustment we just talked about, that's what allows for the seamless hot swapping of textile modules and keeps power efficiency optimized. Furthermore, it introduces something called in-band interrupts. Basically, this allows sensors to flag the processor instantly by slightly modulating the rising edge of the clock signal. It's an incredibly clever trick that cuts interrupt latency down by roughly 30 times. It even enables full duplex two-way communication over a simple two-wire thread. It effectively gives the fabric a highly resilient, deeply dynamic nervous system.
Section 6. Conclusion. Systems Analysis Wrap-Up.
We've really looked at an incredible fusion of disciplines today. We've seen how these smart textiles achieve physical resilience by engineering electroconductivity right down into the structural hierarchy of the fiber, and by utilizing clever encapsulation and laundry bags to survive the brutal mechanical stresses of the washing machine. We explored how they hit a new level of digital intelligence by moving the processing directly onto the body itself, all powered by the high-speed, memory-safe architecture of the Rust programming language. And finally, we saw how they managed to maintain a perfectly stable internal network, despite all the constant stretching and hot swapping, thanks to the dynamic, self-adjusting I4C protocol.
You know, the ultimate goal of this entire third generation of wearable technology is for it to basically become completely invisible. It's supposed to just vanish into the weave. Which leaves us with this final provocative thought. As these incredibly complex systems disappear into the background of our everyday lives, how much of your daily computing is soon going to be woven into the very shirt on your back? Thanks so much for hanging out with me on this explainer. Keep asking those big questions, and I'll catch you next time as we continue to decode the world around us.